I'd like to start today's class by revisiting the notebook that we were looking at on Monday, which is this. And just make a couple of comments about what we did yesterday. So, one thing is we were playing around with the coefficients here of the linear classifier, and we talked about how if I double the coefficients, then I get the same boundary, and then we talked about the overall magnitude of the coefficients as we interpreted it in terms of the confidence or the probabilities that come out. So I just want to make one minor clarification, which is that this all worked nicely when the intercept was 0. If I set the intercept to 1, and then I double the coefficients, then, or maybe you couldn't see, but maybe 2010. It did move a little bit, and that's because the whole equation is W transpose X plus intercept equals 0. And if I want to leave that unchanged, I should scale W and scale the intercept so that the whole equation is scaled. So if I have this, and then I double 4 to 2, now everything stays the same. So that was just a minor clarification from last time. The other thing I wanted to add is about the probabilities. So let me scroll down here. So I apologize again for trying to fix that thing unsuccessfully during lecture last time, but here's what I wanted to show you last time, which is the smoother probability surface instead of having these artificial contour lines, which were just an artifact of the plotting. So here's how the probabilities change, and again, they're close to 0.5 around the boundary, and we can interpret taking the sign of W transpose X as thresholding the probability above or below 0.5. And you can see there's a smooth transition away from the boundary, and as you get to one side, you approach 1, meaning fully confident that it's red, and on the other side, you approach 0, meaning fully confident that it's blue, because probability of blue is just 1 minus probability of red. And then all the rest of the demos looks a little bit nicer. So if I scale the coefficients, multiplying them by 10, now we get this very sharp transition. So we have this interpretation of the coefficients and the intercept. We have this interpretation of the overall scale. It's the same decision boundary because, again, we just scaled everything. So the solution to the equation W transpose X plus intercept equals 0 is unchanged, but the values coming out are now bigger. And so when they get converted to probabilities, they get converted to more extreme values. And you see this very sharp transition from fully confident on one side to fully confident on the other side. And on the other hand, if I make the coefficients small, then we get this kind of slow transition, and we're hovering around 0.5 for quite a big region near the boundary. So one thing, not the only thing, but one thing we can think of regularization as doing, since it makes the coefficient smaller, it pushes you towards this situation and away from this situation. As we'll discuss today, or as will be evident by the end of today, if the data set's separable, then when you have no regularization at all, it actually just wants to make the weights as big as possible. So it'll kind of run away, and so you need regularization to deal with that. But I also wanted to add that regularization also moves the boundary. So it's not like you're keeping the boundary at exactly the same place and just scaling these things. In this case, I am doing that because I'm scaling the coefficients by hand, which isn't exactly the same thing as applying regularization. And the last thing in terms of cleaning up from Monday was just that I had to rush through this sigmoid curve a little bit, so I just want to quickly say again that the point of the sigmoid is that the output of the linear model W transpose X is any number, and we are seeking a probability between 0 and 1, so we need to squash that number to be between 0 and 1, and this sigmoid does it for us. And we can see from this picture why what we saw above was happening. When the coefficients are really big, then we're pushing ourselves to the extreme left and right here, which means probability is very close to 0 and 1. So we're not spending much time in that transition region. Fed.
Is the slope of the linear part of the sigmoid equal to the slope of the plane that kind of comes out of the page from W transpose?
Okay, I think what you're asking is the slope of the sigmoid 1 in the middle? Like, is there a 1-to-1 trade-off? I don't know off the top of my head. Maybe. Yeah, you can just take the derivative, plug in 0, and find out. Probably not 1. I don't know. Yeah. Maybe you can just eyeball it. Any other questions? Okay, so that was stuff left over from last time.
Small question, actually.
Oh, Allie, yeah.
So when we divide, when you did that stuff up where we're scaling the coefficient on the intercept,
Yes.
Is that equivalent to changing the denominator of this equation? To change it to like 1 plus e to the like minus alpha x for some alpha, let's say? Or 1 over
Yes.
e to the minus something.
Yes, if scaling the coefficients is like saying 1 over 1 plus e to the minus alpha w transpose x, and then I'm just changing alpha. Because alpha is just directly multiplying w transpose x.
Okay.
And I didn't write the intercept there. As I said, I'm occasionally sloppy about not writing the intercept. Okie dokie. So, right. The whole point of what I'm trying to do this week is to spend last class on what do these classification surfaces look like when we're using linear models, and not say anything about how do I train it. And today we need to talk about how do we train it. In other words, how do we decide which boundary is better than which other boundary? In other words, what loss function should we use? See, I'm not the only one who got a haircut. Okay. So, how about this? Why don't we just use squared error as our loss function? Well, I want to explain why this isn't a good idea for classification. So what we could do is just say we're encoding our y values as +1, -1. Let's just try to make the thing as close to that as possible. And the reason why you might think that's a good idea is we're just going to look at the sign in the end. So if I was getting 0 training error with this loss, I would be getting perfect classification accuracy, because if y was +1, I would be predicting +1, which would then get thresholded to be positive, and I would guess correctly. So that's fine. So these first two things look reasonable, which is saying if y is +1 and I predict positive 0.9, the error is small. Good, because that's a correct prediction. If y is +1 and I predict negative 0.8, the error is rather large. Good, because that's an incorrect prediction. I looked at the sign and it was negative, but the true class was positive. Here's where things start to break down. If the true class is +1 and I predict 100, I have a huge error, and yet I'm actually getting it right, because I threshold to +100. I'm taking the sign of the output, and I'm getting it right, and yet the loss says I'm super unhappy about what's going on here. Please change W to make me happier, right? But actually, the prediction is correct. So that's fundamentally the problem with using squared error. And we're going to run with this intuition throughout the whole lecture today. So squared errors, least squares is penalizing for being too right. Right, meaning it was positive when it should have been positive, but it was huge, and that shouldn't be a big deal. Okay, so let's look at this in a picture. So you have some feature, and you're doing classification, and you're encoding the y values as only +1 or only -1. The axes here are not one feature and another feature. The axes here are, we only are talking about one feature, and then the y, which is not really an interesting axis here because we just have +1, -1, but we want to draw this picture because y is usually an interesting axis when doing regression. So here's a good line because it crosses 0 at the right place. Remember, we're only looking at is the output positive or negative. So the green line is positive in the right place to predict positive, and the green line is negative in the right place to predict negative. And so this thing gets 0 training error. Actually, before I proceed, anyone not see why this green line is getting 0 training error? I kind of feel like we talked about this last time, but now I don't remember. Maybe not. It would be a good time to ask if you don't see why the green line is correctly classifying these points.
So it's correct because the emails are not spam on the left side of the green line and are spam on the right side.
Right. It's correct because we only care about where the green line crosses 0 because we're just looking at the sign of W transpose X, in this case just W times X because it's just a scalar. And so we care about where does the green line cross the x-axis, and then our predictions are going to be -1 on that side and +1 on that side. Okay, so the thing is, if I actually ran least squares on this, I would get, I don't know, something like this orange line. I guess I could have coded it up and we could have seen what you actually get, but there's no reason to believe you would get the green thing because the green thing way over here is getting huge errors with those points far on the right. It's exactly the problem we talked about. Whereas the orange line doesn't have any giant residuals that are then getting squared. So even just eyeballing this, it looks like the orange line would have a lower loss, and yet the place where it crosses 0 is not the place where we want. So what I'm trying to argue here is don't just use the squared error for classification. It doesn't make sense for classification. And here's an example where we know the green line is doing a better job of what we're trying to do, but the orange line has a lower loss and therefore would be selected, which doesn't make sense. So again, going to this idea of good errors versus bad errors. This is not like an official technical term, but for the purposes of today, the orange line, there are some residuals there where the orange line is actually misclassifying the points. But there are also these residuals being added to the loss where you're not misclassifying points, and those ones are way larger for the green line. Right. Okay, I roughly talked about this already. Okay, now get ready for a new type of diagram, which is the critical thing for you to take away from today is to understand the type of diagram that we're about to look at. And commonly, last year, people struggled with interpreting this type of diagram, but it's important. So look at the axes. The axes are W transpose X on the horizontal axis. That thing is a scalar regardless of how many features we have. So I talked before, when we talked about gradient descent, about, I guess, the data space and the parameter space in these different diagrams. This is yet another type of diagram specific to linear models where I have W transpose X, which I sometimes call the model output or raw model output before I've done stuff to it to get classes, such as thresholding it. And on the y-axis, I have my loss. Okay, so we have not yet made such a diagram. Let us further assume that we're talking about a particular training example whose true label is -1. Okay? So if a training example's true label is -1, then anywhere on the left-hand side, when W transpose X is negative, that's a correct prediction. And anywhere on the right-hand side, that's an incorrect prediction. So This is another way of saying what we've just been talking about of why least squares is not good. Because least squares is just a quadratic between the true thing, -1, and how far away am I from -1. And it doesn't care about classification. It's a loss function meant for regression. So if the thing that comes out, W transpose X, is exactly -1, it's happy. And then it just grows away from that. And I'm not too upset about it growing on the right, because that means I'm getting the answer wrong. And sure, a big loss is fine, but I am upset about it growing on the left, because I'm still predicting -1, because I'm just thresholding W transpose X, but I'm incurring a huge loss. So this is just another way of communicating what I communicated before with the green line and the orange line, but it's a very effective type of visualization for the rest of today's class. Right, so I add this slide here just getting you ready for this type of diagram, even though we also talked about it. I guess one thing I didn't mention yet is that the loss is a sum over training examples. All the losses we've ever seen is a sum over training examples, but this picture is just showing the one term of that sum. It's saying, let's talk about a particular training example that has a right answer, be it positive or negative, and we'll just plot that term of the loss. So it's a very specific type of diagram, and one of the reasons this slide is here is for you to refer to it later if you're having trouble interpreting this diagram. And everything I showed you there would just be mirror image around the y-axis if the true label was -1 or versus +1. Okay, so this slide is the same as the 2 slides ago. I just showed the new type of diagram, had a slide talking about it, and then showed it again. So now that I've talked about it, this would be a good time to ask questions about this diagram. We will just be going on and on and on about this type of diagram for the next 20 minutes. Masood.
I don't understand. Why do we have bad error at the left? Good error.
Why do we have bad error on the left? Okay. A good loss should be big when the thing is doing a bad job of what we want it to do, and small when it's doing a good job of what we want it to do. The x-axis here is W transpose X. The way we make prediction, what we talked about on Monday, is we're going to get ourselves W transpose X and then look at the sign of it. Thus, if I'm on the right half here, it means I'm predicting +1 because W transpose X is positive. If I'm on the left half here, it means I'm predicting -1 because W transpose X is negative. So here I'm wrong and the loss is high. That's fine. There's nothing, losses are allowed to do that, right? That's fine with me. Here I'm right, and the loss is eventually high, and that's the messed up part. There's a question over here, maybe? Fed?
So along this axis, you're changing W. You have different values of W, or?
Well, the thing is, W is a d-dimensional vector, and I cannot show you W. But I don't need to get the point across. I just need to show you the scalar W transpose X in order to talk about what I want to talk about. Okay, so for those who think, oh, we'll just use absolute value error because it's some past lecture in the course that solved whatever problem we were having, that doesn't solve the problem we're having today, because it's still growing towards the left. Okay, let's look at this whatever color that is, the curve that appeared most recently on the slide, that's the 0, 1 loss. That loss takes on a value of 1 when we are wrong, and 0 when we are right. Now, I said before, this is the loss for one training example. So if I'm summing this over all training examples, I'm going to sum 0 plus 0 plus 1 plus 0 plus 1, whatever. And the total will be the number of ones, will be the number of mistakes I made. Thus, the notion of classification accuracy, or error, like we've talked about since the beginning of the course, how many times did I get it wrong, can be expressed in this diagram as this curve, the step function. And we'll call that the 0, 1 loss. The 0, 1 loss does not have the disturbing properties of these other losses because it's just happy when you're right and unhappy when you're wrong. I mean, how great is that, right? However, as you might be thinking, this thing is not smooth, convex, continuous stuff that we need to actually get the job done. So this 0, 1 loss represents, we would be happy if we could minimize it. We probably cannot minimize it. So the whole rest of today is, let's try to smooth this thing out to not have these weird properties, but also be smooth, and then we will arrive at what are called logistic regression and support vector machines. Ali.
Why does it not jump at y equals -1?
Why does it not jump at y equals -1? Because the way we make predictions is we take the sign of W transpose X. So if we are on this side, in other words, what we predict changes when we cross 0, not when we cross -1 or +1. So did that answer your question? Yeah. Tom.
You have the concept of being 2 right, but you lose the concept of being 2 wrong here.
Yes, great. Tom, thank you very much. Tom says we got rid of the concept of being 2 right. Great. But we also got rid of the concept of being 2 wrong. And actually, maybe we would like to penalize that more. And indeed, we will in a minute with the new losses. OK. Said this. You can write it in a clever way. Fine. Talked about this. Talked about that pretty much. I think the last point is the most important one here. The reason why this thing is not usable is not the same reason why squared error was not usable. They have different problems. That's important for you to understand. The squared error did not reflect what we think of as a good or a bad model. The 0, 1 loss does. We just can't optimize it. OK. Let's go to the notebook. OK, first, I'm just going to show you the same diagrams we've been looking at, but with a very slight tweak. I've just played a little game here with the x-axis. I've multiplied it by yi. Before I was saying, well, I had the plot looking one way if the true answer was -1, and then the other way if the true answer was +1. So I had kind of mirror images of plots. I only showed you one of them. But we can play this trick, and that's why I was saying on Monday that let's intentionally encode y as -1 +1 instead of 0, 1. We can do these nice little algebraic tricks. So what is that thing, yi times W transpose xi? Well, if yi is +1 and W transpose x is positive, then it's positive. So getting it right is positive. If the true thing is +1 and W transpose X is negative, the product is negative. So negative means wrong. Likewise, if the true yi is -1 and I predict positive, I'm wrong. And the product is negative. And if they're both negative, I'm again correct, and the product is positive. So it's a little of a bit of a detail, but the point is, if you play these kinds of games, you can just write things down in one shot instead of saying there are these two cases. Because now we're going to come up with some losses, right? And the last thing I want to do is say, well, not the last thing, but something I don't really want to do is say this loss is this if y equals +1 and this if y equals -1 summed over all examples. It's just cumbersome. But by doing this multiplication by a number that is either +1 or -1, I can just deal with it, not have to be a piecewise or case-by-case function, and just say the right-hand side means I'm correct, and the left-hand side means I'm incorrect, and this is a 0-1 loss, and there's no more flipping to worry about. So it's just a mathematical detail, a matter of convenience. If you missed that, you can review it later, and it's not that critical for everything we're about to do. It just makes things prettier. And I've used this notation f sub I of w to say the term of the loss for the ith training example, and the whole loss will be the sum of these little losses, which is the form we've pretty much always looked at in this course. Loss is sum over examples of something. Okay, so we've seen this. We saw that before, just drawing it again. Oh, but it's not shifted. How bad is that? Ah, okay. Okay, now we get into the punchline of today, which is I present to you two losses which have the properties we want and are convex, and we can optimize them. Behold. So the first one is called the logistic loss. And it normally has better parentheses than that. The second one is called the hinge loss. And here they are. Actually, I'm going to put the 0-1 loss on this picture for you as well. I think that would be nice. Let's add that in. Even though it'll make things a little busier, it'll be worth it. Okay. There's the 0-1 loss, which is the thing we wanted. And here's basically what Tom was asking for. Now remember, now the bad errors are on the right-hand side. I should have just done it like this from the beginning. Now I've flipped it all on you guys for no reason. But now we don't have this bad error thing over here that you get a big loss when you're correct. But you do have, as Tom was demanding, the good error thing that it goes up. And my personal take on this is that I like to think of the gradient. The thing is that the gradient of f is the gradient of a sum over examples of something. And the sum and the gradient are interchangeable. So the total gradient is actually the sum of the gradient of the little thing inside. So it actually helps me to think about the derivative of this thing. And one way I think about this 0-1 loss is wherever I am, if I jiggle things a little bit, it's flat. So it's like I don't have a signal or a gradient. And it's a little hand-wavy, but it helps me think about these things. Whereas the reason why it's a little hand-wavy is because we're optimizing with respect to w, but we're just plotting the scalar w transpose x. But nonetheless, with these, I feel like I can kind of slide down the hill with my gradient descent and get where I want to be, which is on that side. Philip.
Why is the hinges 0 at 1 this time, not at 0?
Haha. Why is the hinge at 1 and not at 0 for the orange curve, right? Yeah, that is on the agenda for today, don't worry. Let me just change the order so the orange shows up on top. There we go. Okay. I'm going to go back to the slides and then maybe come back. Oh, I'll do this first. Okay. Why not? With support vector machines, okay, I should say something. Support vector machines are this hinge loss, this orange curve, plus L2 regularization. Logistic regression is the logistic loss, this green curve, typically plus L2 regularization as well. Or some regularization, how about that? This hinge thing, it becomes completely flat, which I kind of talked about just now as something that bothered me a little bit. So I want to explore in depth the implications of the differences between the green curve and the blue curve. Because one thing that I want you to understand coming out of this course is A, that linear SVMs, SVM being support vector machine, and logistic regression are very similar. They're cousins. They're both linear classifiers. I want you to have that in mind. But I would also like you to have in mind a little bit what the differences are between them. And this change in loss, even though they both have the same shape, they don't have the bad errors, they have the good errors. There are deep implications of just this slight difference in the two curves. And here's how it works. If you have a training example that is, you're just doing a great job on it, okay? It's +1 and you predict some positive number, some big positive number. You're not even close to getting it wrong. That's over here. That's this flat part of the orange curve. That point is contributing 0 to the loss. Its loss is 0, and its gradient is 0. That means if I just took that point and threw it away, nothing changes, because it's not actually showing up in the loss. It's just way over here. The orange curve is just flat. I could move the point a little, nothing would happen. I could throw it away, nothing would happen. That's interesting and not something we're used to seeing. And for example, not something that is true for, say, linear regression. That certain points in my data set, I'm so good at getting them right that I could just ignore them. And that's what's special about support vector machines. And the word support vector refers to all of the other points, the ones that do matter, which is a little confusing because to me what's unusual about this is that some of the points don't matter, and yet we use the word support vectors to talk about the ones that do matter. So when I say support vectors occur or are defined when is less than 1, that means all of these things in here. If something is not a support vector, meaning it lives over here, then its loss is 0 and it is pointless. Yeah, there was a question over there. Is it? What's your name again?
Oh, Jeannie.
Jeannie, yeah.
I was wondering for a gradient descent, if we're going down like the lot, when do we go into stop?
Are you talking about for the orange curve?
For a green one.
Yeah, oh, right. Okay. So Jeannie was asking for, say, the green curve, logistic loss. How do we know when to stop? Why don't we just slide down the curve forever? So there's two answers to that. The main answer is that the overall loss that I'm taking the gradient of is the sum over all training examples. And this picture is just for one training example. And while if I'm the only training example in the world and I'm over here, sure, I can just move the boundary farther and farther and farther and farther, and I'll be more and more and more right, and that'll be great. But actually, there's different examples kind of fighting with each other. And so overall, you're going to get somewhere. However, it turns out if the data set is linearly separable, then you're right. You still are vulnerable to this runaway effect. And having a good boundary that properly separates the two halves, you just want to make the weights as big as possible because there's no conflicting and you just want to run all the way like you said. And regularization is what's going to stop that from happening. Because going all the way that way means making W bigger and bigger in magnitude, because you're not changing X in magnitude, right? So if you really want this thing to be huge, you have to make W huge, and regularization will stop that from happening. Good question, thanks. Okay, support vectors. So, my other students in MDS told me that sometimes it stresses people out when I keep commenting that I'm running out of time, so I'm just going to keep it to myself. You enjoy the show. I'll worry about the time constraints, okay? So look at this. Scikit-learn returns this. The indices of the points that are support vectors, and I have provided you with this picture that circles them in yellow, okay? So according to scikit-learn, those yellow things are the support vectors, and it makes sense because those are the ones near the boundary. And the things I said would be not support vectors were the things that I was getting right really well, which are the things that are correctly classified and very far from the boundary. And there are all kinds of effects here, like how far is far. That depends on regularization. There's plenty to talk about here. But check this out. I'm claiming that, so I'm going to do some stuff, make a list of support vectors and not support vectors. And here's what I'm going to do. I'm going to make a new data set where I'll just delete all the points from the training set that were not reported to be support vectors, aka those things way out here. And here's the key lines, okay? I'm not lying. I'm training this thing on the new data set with all those points deleted. And then I'm going to plot that thing, SVM3. And it's, I guess, a bit hard to scroll up and down, and it's going to be hard to make it fit. But let me get rid of this. The point is it's the same curve. Okay, let's look through it together. It's passing through that triangle that's kind of over there. Oh, that's sad. Why does this always happen to me? I didn't run this. I didn't run this cell. Look, it was okay. That's from okay. There we go. It wasn't even the same data set, maybe. Okay, good. It's just under that triangle there, the lowest red triangle, and it's just under the triangle here. Okay, Jupyter is a little tricky because sometimes you forget to run some of the cells. And I'm still plotting all the points because then it'll make the axes the same, but those points aren't actually used. So I could plot really just this data set. It's just harder to see that's the same curve because it shrunk the bounds of the thing. But okay, I'm just doing this to show you that what I said is true, which is kind of cool because it's this, starting from this very abstract picture of loss of one example versus W transpose X times YI, whatever that thing is, just staring at that thing and thinking to yourself, oh, there's this flat part. I wonder what the implications are of that. Maybe this thing doesn't matter. And then all the way to running some code and seeing that that's actually the case. And on the flip side, and this is, I guess, the less surprising part, is that if I actually remove a support vector, so I X'd out the one that I removed, then the boundary actually does shift. And in fact, it shifted away from the point that I removed because the pull of that point was no longer there. Fair.
So support vector you said is Wx minus 1 minus yi has to be less than 1, right? And that's, you call that a support vector. So does that mean you first train?
Yes, thank you. Okay, I do not know what the support vectors are until I'm completely done training.
Okay.
Support vectors are defined as yi w transpose xi less than 1 for w the best w. That's a good point. Yes. I can't just, yeah. Let's leave it at that. Okay. Okay, well, that's not going to happen. So let's go back to the slides. So the next 4 slides, as it says here, they're just for you to refer to, but we've covered everything. And then they're just older slides that I've replaced with the notebooks. 1, 2, 3, 4, something or other. Good. Okay. So the hinge loss, here's how you actually write it. The way to write the hinge, we've talked about this max notation. I promised you it was going to come up at some point, max of 0 and something. Here it is. So you can think of it as a convex upper bound on the 0, 1 loss. It was kind of sitting just above the 0, 1 loss. So it sort of does what we're hoping, and if we perfectly classify all the points, the loss will be 0, because we'll all be we can get ourselves in that flat part. What is called a support vector machine is actually the thing on the bottom. It is this hinge loss plus L2 regularization. Oops. Okay. Okay. We will get there. Now to, was it Philip who asked about this? The location of the hinge? Yeah, okay. It was Philip who asked about this. So why do we have the hinge? Why not have the hinge at 0 instead of 1? Why have the hinge at 1 instead of 0? If the hinge was at 0, then the optimization problem becomes uninteresting, because I can just set W equals 0, and then the loss is just 0 every time, and I'm just adding up a bunch of zeros. But W equals 0 is not a serious boundary. It's kind of like a trivial solution that messes things up. In my sliding down the hill way of thinking about the world, it's like it's telling you to slide down and stop just at the point where you haven't actually made a decision between I'm predicting this or predicting that, because 0 is kind of the boundary, right? So if we move it over a little bit, then we say keep sliding a little more until you're definitely predicting the right thing. That's just another way of thinking about this. And the 1 is arbitrary, so changing the 1 is just sort of a rescaling of the overall problem, or a rescaling of W or something like that, and it's not interesting. It's just the easiest number to pick. Okay, here's the form of the logistic loss. When we use this thing, it's called logistic regression. It is nice and smooth. This thing we actually know how to optimize, and you will do it on the assignment that's currently out. And it's just you guys know the drill by now. You take the thing, you take the gradient, you optimize it. The hinge last one was a little bit trickier because it's not smooth. Okay. These things are used a lot. I think I mentioned last time they're used in Gmail for predicting spam or importance, or maybe both, but all kinds of things. Later we'll talk about stochastic gradient descent in the course, so you can apply this here and scale up to very big data sets. But the important part is they're simple, right? They're linear models. So we can scale these things up and they still work, and we can understand how they work, and they're kind of appealing in a bunch of ways. Although you might not find it appealing that they can only learn linear boundaries, and we'll talk about that on Monday. Okay, important point that I also forgot to say on Monday, even though this more goes with Monday's lecture than today's lecture. For linear regression, we had this intuition. What does a weight mean? It means this feature matters this much. If I increase feature 5 by 1 unit, then I increase my prediction by W5 amount. If W5 is positive, it means as I make this feature bigger, I expect the output to be bigger. If it's negative, it means if I make this feature bigger, I expect the output to be smaller. We can bring with us a lot of things we know from linear regression to linear classifiers. For example, if this thing sets W5 equals 0, it's basically saying that feature doesn't do anything, just like with linear regression, because I'm just taking 0 and multiplying it by that feature, just like with linear regression. And then we can have L1 regularization and use all the same kind of thinking that we used from before. And indeed, you will do that on the assignment. All that stuff just kind of carries over because at the end of the day, it's still just W transpose X. It's just a different loss. Philip?
So if they're both so great, when would you use logistic regression instead of the support?
Yeah, if they're both so great, when do we use which one? So I think that may even be in the later part of the Jupyter notebook. But on Monday, we're going to talk about kernels, which work better with SVMs for computational reasons. And those allow us to fit nonlinear boundaries. With logistic regression, we get more natural probabilities coming out of them, which is nice. The optimization problems are different. I don't know all the details, but they must have different properties in terms of scaling. And there's also, some people like to talk about SVMs, about this max margin thing that I'll get to in a minute, although I don't know if it's really that critical. I guess in general, if a linear SVM worked reasonably well on a problem, I would be surprised if logistic regression was completely horrible on that same problem because they are the same model with a bit of a different loss. Oh, also the way we're going to extend them to multi-class, we're only talking about binary classification, is also a bit different, and we'll talk about that on Friday. Okay. They're good. And they're good, and all the stuff we know about linear regression we can apply, not just the tools, but the intuition. That's very useful. Fine. Okay. So someone tried out a bunch of classifiers on a bunch of data sets and found that random forests worked well on most and SVMs on the second most. Again, we have this no free lunch theorem, so what's best will still depend on the problem, but they tend to work well for the types of problems humans try to solve. And this RBF thing we'll talk about on Monday. Okay, so max margin. I'm not a big fan of this approach to SVM, although that's how I originally saw it first. So this is sort of like the perceptron. I want to say it so that I send you all out into the world having heard of this. But I personally don't think it's that critical. It's just another interpretation of what we just talked about. It's no new stuff. Okay, so here's how it goes. Take a linearly separable data set. We talked about perceptron briefly. It finds some hyperplane. Here's one. But there are a bunch of hyperplanes that could get zero training error on this data set, and you might ask yourself, which one is the best one? And the red one looks like you're kind of cutting it a little bit close here. Like, I'm getting very, very close. What if there's a little bit of noise in that point and I'm actually wrong, or who knows, right? I'm just going right next to my training examples. And the blue one is sort of playing it safe. You're leaving yourself this margin of error. So the margin refers to the distance between the plane or hyperplane and the closest training examples to it. So this is showing you the margin. It's a distance. And as it turns out, you can prove that the SVM loss, the hinge loss plus L2 regularization, gives you back the separator that maximizes the margin. This bothers, the reason why I'm not such a big fan, this is actually amazing in the sense that we just have this hinge thing and suddenly, boom, we get the middle-most classifier. That's interesting. We'd have to think about that. But A, most data sets are not linearly separable. And B, to get from the math, to get from this max margin math to the hinge loss math is a little trippy. So I think it's in the bonus slides, but I don't think it's necessarily worth doing. OK, only 1 minute left. That's fine. We're okay. So no worries. Yeah. This is more stuff about max margin. Okay, that's fine. Not critical. So today we talked about the hinge loss and the logistic loss. And they both solved this problem we had. We didn't like least squares because it really penalized doing a great job. Well, that never sounds good. We didn't like the 0-1 loss because it wasn't convex, smooth, continuous, blah, blah, blah. So we have some new words, SVMs, logistic regression. We have some new losses that they're matched up with, hinge loss and logistic loss. And this is Mark who wrote this, but a lot of ML consulting just boils down to find good features and then use regularized logistic regression. I've noticed too that it often works very well, even though it's so simple. And again, you might think, how could a linear classifier do anything? And it all comes down to this issue of finding good features. If you find good features, then just cutting the thing in half often does a very good job. And that is it. So I'll see you Friday.